Welcome to the session Ductility for Earthquake Resistant Structure. This is C.G. Konapure, Assistant Professor, Department of Civil Engineering, Walchand Institute of Technology, Solapur. So this is the learning outcome that at the end of this session, students will be able to describe the requirement of ductility for earthquake resistant structures. So if you observe, there is moment curvature relationship for beam under flexural stress. So ductility, what is ductility? It is from the structural point, it is the ability of the member to deform beyond its elastic limit without failure. And IS code actually assumes or enforces minimum ductility specification. If you observe, the moment curvature relationship for two types of members are specified here. One is ductile member, second is brittle member. Up to elastic limit, both the members are behaving in the same manner. But brittle member, the rotation capacity or deformation capacity is very low. That's why it has failed here at this red point. But in case of ductile member, the rotation capacity is very high. That's why this much rotation capacity is improved as compared to the brittle member. So ductile member's rotation capacity is very high as compared to the brittle member, and that's why it is required in earthquake. Now this is the objective of ductility provisions. What is the objective? One is a large capacity for inelastic deformation. Second is it provide reliable and consistent inelastic capacity. What is the capacity? Capacity of the different members and structural system, it should be predictable. Now the next objective is that it prescribes the relative strengths of the different members to control failure mechanism at joints. So control of the failure mechanism. So it is bound to happen that the failure is coming there, but the control on the failure mechanism that must be prescribed. Ultimately, the objective is that we must permit the structure to undergo large inelastic deformation before collapse. So fail-safe design philosophy is expected here. Building can be designed for lower forces if ductile behavior is ensured. In a second way, I want to explain this statement that if we are designing our structure, already the structure designed for the lower structure, so we have to ensure the ductility for the survival of the structure. Now ductility detailing provisions are specified in IS Indian Standard 13920 2016, and which require special confinement of the concrete in following zones. Especially these are the members: RCC beam member, column member, beam column joints, shear walls, coupling beams. Now the confinement means what? Confinement of the concrete, because concrete is the heterogeneous material, concrete is a brittle material, and that concrete has to be confined with some confinement, and that confinement is provided by closely spaced stirrups. Now the design spectrum is modified based on inherent ductility of structural system. So if you refer IS 1893, in which design spectrum is given, but inherent ductility of the structural system is modified by modifying the design spectrum, and the response reduction factor, which is used for these different types of the structural system, and their factors are specified here. Different systems are provided here, and that is the ductile moment resisting RCC frame, a factor is 5, ordinary RCC shear wall factor is 3, and for different types of structural system, the R response reduction factors are specified in this table. Now my question for all of you: what is the response reduction factor for ductile shear wall? As in the earlier slide, I have explained different structural systems for different response reduction factors. So what is the factor for this? There are 4 options: A, B, C, D, 2, 3, 4, 5. So you give the answer and pause the video, give the answer, and then continue. The answer is D, that is the response reduction factor R is 4 for ductile shear walls. Now this is one important, I would say, the message. Higher ductility implies lower design forces but greater acceptable damage also. One more message: higher ductility implies greater damage to non-structural elements and services. Non-structural elements means those who are not sharing the load, who are not capable of sharing the loads, bending moment, shear forces, deflection, deformations, especially service lines or service elements. Now, special ductile design requirements. What are the requirements against or for the special ductility? That is the location of plastic hinges. Now, location of plastic hinges means the mechanism is forming in the structural members, and that is in the form of a permitted damage. And these plastic moment hinges formation in the column results in substantial reduction in the vertical load carrying capacity. It should be avoided. Plastic hinges shall not form in the columns, so load carrying capacity of the entire structure that will reduce. Second is by providing this concept that strong columns compared to the beams, one can control the location of possible plastic hinges formation. Now, if you observe this diagram in which there are two frames shown and location of plastic hinges are shown in both these two structures. For in first structure here, column sway mechanism is shown in which plastic hinges have formed in the columns. Now, if the plastic hinges are formed in the columns, probably the column will separate in two parts, and the structure or the floor above will come down, so which is not permitted. Second is this design frame behavior. It is expected, and in this beam are subjected to the plastic hinges, or the plastic hinges formed in the beams, and beams are very good in inelastic deformation. So if beams are failing by the plastic hinge formation, then columns will stand as it is and the column will not fail and floor will not come down. That's why this is desired frame member. This is expected, and that can be controlled by permitting the formation of plastic hinges. Now the control of sequence of failure. Now how we can control? That is by giving the proper design aspect. We can provide the strong columns as compared to the beam sections. So beam section and column section shall not be same. As far as safety concerned and the failure mechanism, failure sequence, column should be more stronger than the beams. Now what is the sequence? Any failure in the structure, first failure must be flexural failure in the beams, means beam by bending action, that must fail first. Second, then beam shall fail in a shear mode. So direct shearing of the section that is allowed in a second at second order. Third is flexural failure of the columns or buckling of the column, that is admissible. Fourth is shear failure in the columns, and finally beam column joint. So if anything is failing in the beam column joint in the structure during the earthquake, that must be at the end. First beam shall fail in the flexure, then the beam shall fail in the shear, column shall fail in the flexure or buckling, column shall fail in the shear, and finally beam column shall fail in the beam column joint shall fail. Now calculation of this capacity of section as designed to ensure the above order, that is possible by providing the design as per IS 39/2016 provisions. So if you use those provisions, probably definitely we will get this sequence of the failure in this manner. Now these are the references for this video. Thank you.